Exercises acid-base, Part 7, titration of monoprotic acid and monoprotic base. Exercise 49, recognize the titration of 50 ml of acetic acid solution with the base NaOH. Noted X equal Vb divided by the Vb at equivalence is the degree of progression of the titration. Write the titration reaction. So we have reaction between weak acid and the strong base. The reaction is always complete. Acetic acid CH3COH plus OH minus gives CH3COO minus plus H2O. Calculate the pH of the final solution for the following additions. We start with Vb equals 0. So before addition of the base, the solution contains only a weak acid, acetic acid. So the pH of the solution at the starting is the pH of the weak acid. We have to compare C0 with respect to 100 Ka, and the relation C greater or equal 100 Ka is valid. So apply directly pH equal half pKa plus PC0 or half pKa minus half log C, and we put pKa and log C with their values, and the pH is equal to 3.5. Now, what is the pH when we add 12.5 milliliter of the base, or for X equals 0.5? So we have a reaction. We have a reaction between the acid and OH minus, and a part of the acid CH3COOH was transformed to the conjugate base CH3COO minus. The number of mole of the acid is equal 0.25 millimole. That of the base added is equal to the concentration of the base times the volume added, which equal 12.5. So we have 0.125 millimole. In the final solution, HA will be transformed to A minus. So we will have HA plus A minus, and therefore we can apply Henderson formula, pH equal pKa plus log concentration of the base at equilibrium divided by the concentration of the acid at equilibrium, or pH equal pKa plus log number of mole acetate divided by the number of mole of acetic acid at equilibrium, since V total is constant. And we transformed 0.125 will transform half of HA, so we will have formation of acetate equal to acetic acid in the solution. Therefore, pH equal pKa 4.74. Or another method, for X equal 0.5, so we are at the half equivalence point, and at the half equivalence point, you know that pH equal pKa of the couple involved equal 4.74. What is the pH for a volume equal 25 milliliter? In any problem, acid-base titration, the first step to do is to calculate on the draft the volume at equivalence. So in this problem, V equal 25 milliliter, or for X equal 1, this is the equivalence point. And you know, at equivalence point, all acetic acid has been transformed to its conjugate base acetate. So at equilibrium, acetic acid at equivalence point, acetic acid plus OH minus give acetate plus H2O, and this reaction is complete, starting from 0.25 acetic acid, which is the number of mole initial, and OH minus added, so at volume 25 milliliter, we multiply by the concentration of the base, so we have 0.25 millimole. So at equivalence, acetic acid and OH minus will react completely, and we have formation of 0.25 millimole of acetate. So what is the concentration of acetate at the equivalence point? The concentration of acetate at the equivalence point is equal to the number of mole of acetate at this point divided by V total. And V total is equal to V0, which is 50 ml, plus the volume added, which is 25 ml. So equals 0.25 millimole divided by 50 plus 25 milliliter. So the concentration of acetate at equivalence point equals 3.334 10⁻3. So the pH at equivalence will be basic, and this is the pH of the weak base. So we have to look to the domain of validity. If the concentration of the base at equivalence is greater or equal 100 kb of the couple involved, or if the pH is greater or equal pKa plus 1, we can apply directly the relation POH equal half pKb of the couple minus half log C, and we transform POH to pH, so we obtain the relation pH equal half pKw, which is equal to 7, plus half pKa plus half log C. To note that C is the concentration of the base at equivalence. So pH equals 7 plus half 4.74 plus half log, and the concentration equals 3.334 10⁻3. So the pH equal 8.136. If our formula is correct, we have to prove that this pH is greater than pKa plus 1. pKa equal 4.74 plus 1. So 8.136 is greater than pKa plus 1, and this formula is valid. Now we have to calculate the pH of the solution for the addition of 50 ml of the base, or X equal 2. This volume is after the equivalence point. The number of mole of base added equals Cb times Vb equals 0.5 millimole, and the initial number of mole of the acid is always 0.25 millimole. So we write the reaction between acetic acid and OH minus to acetate and H2O. Initially, we have 0.25 millimole of acetic acid, and we add 0.5 millimole of the base. Since we are at equivalence, after equivalence, so all acetic acid will be transformed. So the number of mole of acetic acid remains after equivalence is practically epsilon, which is practically equal to 0. So 0.25 will disappear completely, and OH minus at equilibrium is equal 0.5 minus 0.25, so we will have 0.25 millimole of OH minus in excess, and formation of 0.25 millimole of the conjugate form of the acetic acid, which is the acetate. So in the final solution now we have two bases, OH minus, which is a strong base, and the number of moles is 0.25 millimole, and acetate, which is a weak base, and the number of mole is 0.25 millimole. Since the quantities of these two bases in the solution are close, so the strong acid OH- will determine the pH of the solution, and in this case we neglect the base acetate. OH- in the final solution equals 0.25 millimole and will determine the pH. So we apply POH equal minus log concentration of OH- in the solution. The concentration of OH- in the solution at this addition of the base is equal to the number of mole of OH-, which is equal 0.25 divided by the V total. V total is the V initial taken, which is 50 ml, plus the volume added of the base, which is 50 ml. So the OH- concentration at the volume of the base equal 50 ml is equal to 0.5 10⁻3. We apply the relation, we find POH equal 2.6. pH plus POH equal pKW, so we calculate pH, which is equal to 11.4. In this exercise, part C, give the equation of the pH as a function of x for x between 0 and 1 and for x greater than 1. For x between 0 and 1, so we are before the equivalence. We write the reaction acetic acid plus OH- give acetate plus H2O. Initially, we have Na of the acetic acid and B of OH-. Since we are before equivalence, so all OH- added will react. So acetic acid will be in excess and OH- will disappear completely. So at equivalence, at equilibrium, we have practically 0 of OH-, and the number of moles of acetic acid remained at equilibrium is equal to Na acetic acid minus number of moles of acetic acid reacted, which is Nb. So the number of moles of acetic acid at equilibrium equal Na minus Nb, and we have formation of Nb of acetate. So in the new solution now we have acetic acid and its conjugate base. And I will repeat, since acetic acid and acetate are of weak behavior, so the exchange between acetic acid and acetate will be very weak and we neglect this exchange. So the number of mole of acetic acid and acetate in the final solution are practically the number of moles obtained at equilibrium of the reaction written. We apply Henderson formula since we have the acid and its conjugate base, pH equal pKa plus log concentration of the base divided by the concentration of the acid at equilibrium. So pH equal pKa plus log number of moles. So pH equal pKa plus log base, which is equal to CbVb, divided by the acid, which equals CaVa minus CbVb. Now we have to transform pH as a function of x, so we have to introduce the notation of x. We know that x is equal to the volume added divided by the volume at equivalence. So Vb equal Ve times x, since x equal Vb divided by Ve. So pH equal pKa plus log CbVe times x divided by CaVa minus Cb times Ve X. And we know at equivalence that CAVA equals CBVE. So we replace CBVE by CAVA and the relation becomes pH equal pKa plus log CAVA X divided by CAVA minus CAVA X. We simplify by CAVA and the final relation obtained is pH equal pKa plus log X divided by 1 minus X. Now find the relation between pH and X for X greater than 1. So for X greater than 1, we are after equivalence. That means all acetic acid completely transformed to acetate, and we have OH minus in excess. So initially we have Na acetic acid, we have Nb of OH minus added 0 acetate. At equilibrium, at equal infinity, we have epsilon of acetic acid, which is practically 0, and OH minus is equal to Nb initial minus Nb reacted, so Nb minus Na, and we have formation of Na of acetate. So the solution contains strong base and weak base, and the strong base will determine the pH. The number of mole of acetate equals CAVA, that of OH minus is equal CBVB minus CAVA. So since OH minus will determine the pH, we calculate the concentration of OH minus after equivalence. OH minus equal Nb divided by V total equals CBVB minus CAVA divided by V total, which is the volume of the acid initially present plus the volume of the base added. Then we apply the relation POH equal minus log OH minus in the solution, or pH equal 14 plus log OH minus in the solution. So pH equal 14 plus log CBVB minus CAVA divided by VA plus. So we transform now VB to X, and we know that X equal VB divided by VE, so VB equal VEX minus CAVA divided by VA plus VB is replaced by VEX. So pH equal 14 plus log CAVAX minus CAVA divided by VA plus VEX, and therefore we have appearance of the relation between pH and X. So pH equal 14 plus log CAVA X minus 1 divided by VA plus VEX. In the last part, in part D, draw the shape of the titration curve. Since we have titration of weak acid by strong base, so the pH will start from pH acidic and will increase. We will have a jump. Then the pH is practically constant. So at VE, we have pH basic, and at half equivalence, we have pH equal pKa. Around pH equal pKa, we have the maximum buffer capacity. Exercise 50, we titrate ammonia solution NH3 by hydrochloric acid HCl of concentration Ca. So we have practically the same method of work as exercise 49, but in this case the base NH3 is in the beaker and the acid HCl is in the burette. So question A, write the titration reaction between ammonia and H3O plus, the strong acid. We will have a complete reaction. So NH3 plus H3O plus gives NH4 plus H2. Calculate the concentration of the unknown NH3 denoted by Cb. So at the first equivalence point, we have a number of mole of the base present is equal to the number of mole of the acid added. So CbVb equals Ca Va at equivalence noted Ve. So Cb equals Ca Ve divided by Vb, and Ca equals 0.1 times Ve, which is given 10 ml, divided by the volume of the base taken initially, which is given 10 ml. So the concentration of the base is equal to 0.1 molar. Calculate now the pH of the final solution before the addition of the acid HCl. Before addition of the acid HCl at V equals 0 or X equals 0, the solution contains only a weak base NH3. So the pH will be the pH of the weak base NH3, and we have to look to the domain of validity. We compare C0 with respect to 100 Kb, and Kb is deduced from Ka according to the relation pKa plus pKb equal pKw equal 14. We prove that Cb is greater or equal 100 times Kb, so we apply directly the relation POH equal half pKb plus PC0, or POH equal half pKb minus log C0, implies the relation of POH is transformed to pH. pH equals 7 plus half pKa plus half log C. So pH equals 7 plus half 9.2 plus half log the concentration, which is 0.1. So the pH is equal to 11.1. Calculate the pH of the solution when we add 5 milliliters of the acid. We know that the V equivalence is 10 ml, so Va equal 5 ml is the half equivalence. And the half equivalence point, we know that the pH is equal to pKa of the couple involved, which is NH4 plus NH3, so pH equal 9.2. This is another method of calculation of the pH. We write the reaction involved and we put the table of conversion, but it's easier to deduce directly that pH equal pKa of the couple. Calculate the pH of the solution when 10 ml of the acid were added, so X equal 1. The Va equal 10 ml, this is the equivalence point, and at equivalence, all ammonia has been transformed to NH4 plus. So in the solution, we will have NH4 plus of a new concentration. The number of moles of NH4 plus at Ve at the equivalence point is equal to the number of mole of NH3 initial is equal 1 millimole. So the concentration of NH4 plus at V equivalence is equal to the number of mole divided by V total equal 1 divided V total. We have 10 ml and we have 10 ml of ammonia and we add 10 ml of the acid. So the total volume is equal to 20 ml. The concentration of NH4 plus at equivalence equals 0.05. So the pH is the pH of weak acid. We compare C0 to 100 Ka and we find that the concentration is greater or equal 100 Ka. This relation is valid. We apply directly pH equal half pKa minus log C equal 9.2 divided by 2 minus half log 0.05. So the pH at Va added 10 ml is equal to 5.25. At V equal 20 ml, so X equal 2, we are after equivalence. That means all ammonia in the solution has been disappeared or completely reacted, and the acid HCO plus will be in excess. So we write the table of conversion. NH3 plus HCO plus gives NH4 plus H2O. We have 1 millimole of NH3 and 2 millimole of HCO plus. At equilibrium T equal infinity, NH3 disappear completely, HCO plus in excess equal to -1, and we have NH4 plus 1 millimole. So in the new solution, we have two acids, one strong and one weak, of close or equal concentration or quantities. So HCO plus will determine the pH of the solution, and pH equal minus log HCO plus concentration in the solution. The concentration of HCO plus in the solution equal number of mole divided by V total equal 1 divided by initially we have 10 ml plus V total plus V added, which is 20 ml, so equal 0.033 molar, which is greater or equal 3.2 10 minus 7. So we apply directly the relation pH equal PC0 equal minus log 0.033, and the pH therefore is equal 1.48. By the same way as exercise 49, we will find the relation between pH and X for X between 0 and 1. So for X between 0 and 1, we are before the equivalence point. That means ammonia is in excess, HCO plus limiting, and we have formation of NH4 plus. So in the final solution, we will have NH3 and its conjugate acid NH4 plus, and the pH is given according to Henderson equation, pH equal pKa plus log concentration of the base at equilibrium divided by the concentration of the acid at equilibrium. The number of mole is constant, the volume is constant, so pH equal pKa plus log N ammonia divided by N ammonium. pH equal pKa plus log CbVb minus CaVa divided by CaVa. And we know that CbVb is related to V acid at equivalence. CbVb equal CaVe. So the pH equal pKa plus log CaVe minus CaVa divided by CaVa, and Ve is replaced by its relation with X, which is equal to Va divided by X. So the pH equal pKa plus log CaVa divided by X minus CaVa divided by CaVa. So we simplify by CaVa and we find the relation pH equal pKa plus log 1 minus X divided by X. What is the relation? What is the shape of the titration curve? The titration curve will start from pH basic to pH acidic, since initially we have ammonia. So it starts at 11.1. When we add OH minus and NH3 decrease and H4 plus increase, at X equals 0.5 or have equivalence, which is 5 ml, the concentrations of NH3 and NH4 plus are equal, till the V equivalence 10, all NH3 has been transformed to NH4 plus and the pH will be acidic. Therefore, we will have NH4 plus excess of HCO plus, and HCO plus is the strong acid that will determine the pH. Exercise 54, below the titration curve of unknown base by strong acid HCl, calculate the pH at equivalence. The volume at equivalence and the pH at equivalence are found graphically by the parallel tangent rule. So V equivalence equal 25 milliliters and pH at equivalence equal approximately 5.8. Calculate the concentration of the base. We apply the relation at equivalence. The number of mole of base initial is equal to the number of moles of acid added. So CbVb equals CaVe. Therefore, Cb equals CaVe divided by Vb, and Cb equal 0.2, which is the concentration of the acid, times 25, which is the V equivalence found graphically, divided by the V initial, which is 50 ml. So the concentration of the base is equal to 0.1 molar. Calculate Kb of the couple. We know that Kb and Ka of the couples are related, and the half equivalence point, the pH is equal to pKa of the couple. So at half equivalence point, Va equal 12.5 milliliter, we have pH equal pKa equal 9.3, and we know that pH pKa plus pKb equal pKw, so pKb equal 4.7, and therefore Kb equal 1.995 times 10 to the power minus 5. Calculate the molar mass of the base. We calculated the concentration of the base in the previous parts, and the concentration of the base is equal to the number of mole of base divided by the volume of the solution, equal Mb, the mass of B of the base, divided by the molar mass of the B times the volume of the solution. So the molar mass is equal Mb divided by CbVb, and the mass of the base taken initially equals 0.5001, divided by the concentration of the base, which is found to be 0.1, times the volume of the base taken, which is 50 ml. So the molar mass of the base is equal 100.02 gram per mole. Exercise 56. In the case of titration of weak monoacid HA with a strong base, the pH at equivalence is acidic, neutral, basic, prediction impossible, or none of these answers. We know that HA react with OH minus in a complete reaction to give A minus and H2O. At equivalence, or HA has been transferred to A minus, so A minus will interact with water with incomplete reaction to give HA and OH minus. So we have releasing of OH minus in the solution, and the pH will be basic. So the answer is C. Exercise 57, consider the titration of 20 milliliter of acetic acid with NaOH, a strong base. Calculate the pH for the added volumes of NaOH at 11.35. So this exercise is studied in details previously. We have the concentration of the acid 0.5 and the volume of the acid 20 milliliter. We have the concentration of the base 0.5 molar and the volume added equal 11.35. So at equivalence, the number of mole of the acid present is equal to the number of mole of base added, so CAVA equals CBVE, and we calculated the equivalence point VE equal 20 ml. At VB equal 11.35, so we are before the equivalence. So X is between 0 and 1, and we know that X is equal to the volume of the base added divided by the volume at equivalence. So X equal 11.35, which is the volume added, divided by the volume of the base at equivalence 20. So X equals 0.5675. We return to the relation found previously. We know for X in the titration of weak acid by strong base, and X is between 0 and 1, we found the relation of the pH equal pKa plus log X divided by 1 minus X. So we put X in its value, pH equal the pKa of the couple, which is 4.74 plus log 0.5675 divided by 1 minus 0.5675. So the pH is equal to 4.86, and the correct answer is therefore A. We pass to the last exercise in this session of part 7. Exercise 58. Consider the following titration curve of an acid with a base. Which of the following statements is or are correct? So this is the titration curve. A, it's the case of a weak acid. This is true since we have two inflection points, one at V added equals 0, and another jump or inflection point at the equivalence point. So A is correct. B, it's the case of diacid. This is false because the titration of diacid will give two jumps or two equivalence points. And in this exercise, in this curve, we have only one equivalence point. C, the pKa of the acid is 8.5. We know that pKa is deduced at the half equivalence point. So at the half equivalence point, the pH is around 3.5. So C is incorrect. D, it can be used as a buffer around 3.5. Yes, around pH equal pKa. This is the maximum buffer zone. So D is true. E, it can be used a buffer around a pH 8. E is false. So the correct answers are A and D.